A house in Riyadh, a home in Darwin, a flat in London, and a building in Florida can all experience extreme heat. But the same cooling solution will not work equally well in all four places. The reason is not temperature alone, it is the combination of sun, humidity, wind, nighttime cooling, and the way each building handles heat. Consider one revealing seasonal example. In May, an evaporative cooler in northern India or Pakistan can feel remarkably effective. Hot, dry air passes through wet media, some of the water evaporates, and the supply air becomes cooler. But a few weeks later, the monsoon arrives. The same cooler may suddenly feel far less useful. The temperature is still high. The machine has not changed. So what has? The answer explains almost everything about cooling buildings. There is no single cooling technology for every climate. This is not only a problem for traditionally hot countries, heat waves are increasingly testing buildings in Europe and the United Kingdom, places where many homes were designed to retain winter heat and may have limited external shading or cross ventilation. At the same time, demand for mechanical cooling is rising rapidly across the world. The International Energy Agency warns that without a stronger action, energy use for space cooling could more than double by 2050. Air conditioning protects comfort, productivity, and health, but it also increases electricity demand, especially during the hottest hours when power systems are already under pressure. So the useful question is not simply, can we remove air conditioning? It is, how much heat can the building prevent, and what is the most appropriate way to handle the heat that remains? To understand passive cooling, imagine a building as a heat balance machine. Heat arrives in four main ways. First, solar radiation passes through windows and is absorbed by roofs and walls. Second, heat conducts through the building envelope. Third, warm outdoor air enters through ventilation and uncontrolled leakage. And fourth, people, lighting, appliances, and equipment release heat indoors. A building can respond in only a few fundamental ways. It can prevent heat from arriving, it can store heat and delay its effect, or it can reject heat to cooler air, the sky, the ground, or through evaporation. This gives us a useful rule. A building does not create coolth. It blocks heat, moves it in time, or sends it somewhere else. The first priority is usually solar control, especially around windows. Sunlight that passes through glass is absorbed by floors, walls, and furniture. Those surfaces warm up and release heat into the room. An internal blind may reduce glare, but much of the solar energy has already crossed the glass. External shading acts earlier. Overhangs, shutters, awnings, screens, and balconies intercept sunlight before it becomes an indoor cooling load. Orientation matters too. Low morning and afternoon sun can be difficult to block, so east and west-facing glass often needs particular attention. Roofs are another major solar surface. Reflective finishes can reduce absorbed solar energy, while suitable insulation slows the movement of heat indoors. But insulation is not a cooling machine. It delays heat transfer. It does not remove heat already trapped inside. This is why a highly insulated room can still overheat if it has large unshaded windows, significant internal gains, and no safe way to release heat. Next comes air movement. But two different effects are often confused. A fan mainly cools people, not rooms. Moving air increases convective and evaporative heat transfer from the body, which can improve comfort even when the air temperature changes very little. Ventilation is different. It can remove heat from a room, but only when the outdoor air provides a useful heat sink. If the air outside is cooler than the air inside, cross-ventilation or a stack ventilation can carry heat away. If the outdoor air is hotter, opening windows may add heat instead. Night ventilation can be particularly useful after a hot day, provided the night becomes cool enough. But window opening can be limited by noise, pollution, security, insects, weather, and fire safety requirements. Natural ventilation is therefore not just an architectural opening, it is an operating strategy governed by outdoor conditions. Heavy walls, floors, and ceilings can absorb heat and delay the indoor temperature peak. This is thermal mass. It can be extremely useful in a hot, dry climate with a large difference between daytime and nighttime temperature. The mass absorbs heat during the day, then releases it during cool night ventilation. But thermal mass is like a battery. If it is not discharged before the next hot day, it fills again and eventually becomes a source of unwanted heat. In warm, humid climates where nights stay hot, lightweight and well-shaded construction may sometimes be more appropriate than adding mass without a heat rejection strategy. Now return to India and Pakistan. Before the monsoon, many inland regions experience extremely hot and comparatively dry conditions. India's meteorological records describe places such as Jaipur as dry and hot from March to May, with maximum temperatures often peaking in May. In dry air, evaporation has capacity. When water changes from liquid to vapor, it absorbs latent heat. An evaporative cooler uses this process to reduce the air's sensible temperature while increasing its moisture content. In the right conditions, that added moisture may also improve comfort. But as monsoon air arrives, the calculation changes. Humidity, cloud, and rainfall increase, and the air has less capacity to accept additional water vapor. Direct evaporative cooling becomes less effective. Now, the building may need both sensible cooling, lowering air temperature, and latent cooling, removing moisture. Vapor compression air conditioning naturally removes some moisture as water condenses on a cold coil. In challenging hot, humid conditions, system design and control must ensure enough dehumidification as well as temperature control. The same contrast appears around the world. Saudi Arabia has intensely dry inland environments, but coastal locations along the Red Sea and Arabian Gulf all can face substantial humidity. In the United States, evaporative approaches suit parts of the dry Southwest far better than the humid Gulf Coast and Southeast. Australia contains a dry interior, a tropical north and humid coastal regions, different cooling problems within one country. The correct engineering question is not, which country is this? It is, what are the dry bulb temperature, wet bulb temperature, humidity, nighttime temperature, and water constraints at this location, at this time? Long before compressors, buildings used courtyards, wind towers, shaded streets, thick walls, and carefully placed openings. These ideas were not magic. They manipulated radiation, pressure, buoyancy, evaporation, and thermal storage, and they can still teach us a great deal. But copying a wind tower or courtyard does not guarantee a cool building. Performance depends on geometry, wind direction, surrounding buildings, humidity, opening area, nighttime temperature, and how people actually use the space. The valuable lesson from traditional architecture is not to reproduce its appearance. It is to understand the local environmental logic behind it. For an existing home, the sensible sequence begins with diagnosis. First, identify where the heat is coming from. Is sunlight entering through west-facing glass? Is the roof highly exposed? Are appliances creating large internal gains? Or does the building simply fail to cool down overnight? Second, block avoidable solar gains, ideally with safe external shading. Third, reduce unnecessary internal heat from lighting and equipment. Fourth, use fans to improve occupant comfort with relatively little electricity. Fifth, ventilate when outdoor conditions are cooler and otherwise suitable, not simply because it is summer. Then consider larger upgrades to roofs, glazing, and the envelope, assessed for the local climate and winter performance as well as summer. Finally, if these measures cannot maintain safe and comfortable conditions, use appropriately sized, efficient mechanical cooling for the remaining load. Major building alterations, electrical work, work at height, changes affecting fire safety and ventilation design should be assessed by competent local professionals. The future of cooling is unlikely to be completely passive or completely mechanical. It will be responsive. External shading can adjust to the sun. Windows and vents can open only when outdoor conditions are useful. Thermal storage can shift cooling demand away from peak hours. Fans can cool occupied zones rather than conditioning an entire empty room. Dedicated dehumidification and desiccant systems may separate moisture removal from temperature control. Controls can switch between natural ventilation, evaporative cooling, and efficient air conditioning as weather conditions change. This is the same lesson as the seasonal cooler in South Asia. The building should not remain committed to one mode when the climate itself has changed. There are clear limits. If nights stay hot, thermal mass cannot discharge effectively. If outdoor air is humid, polluted, or unsafe to admit, natural ventilation may not provide relief. Dense urban areas may stay warm long after sunset. Some occupants and building uses require tighter temperature and humidity control. In those situations, mechanical cooling is not a design failure. The failure would be asking it to remove heat that could have been prevented economically in the first place. Passive design reduces the load. Efficient systems handle the remainder. And resilient buildings should remain safer for longer when power or equipment is disrupted. So can buildings stay cool without air conditioning? Some can, for much or even all of the year. Many others can use far less air conditioning than they do today. But the real engineering answer depends on climate, building form, and operation. Stop heat before it enters. Store it only if you can release it later. Use air movement intelligently. And choose cooling technology according to both temperature and humidity. Which climate do you live in? Hot, dry, hot, humid, or temperate with increasingly severe heat waves? And which cooling method works or fails where you live? Share your experience in the comments. It may become part of a future engineering investigation.